Thank you for the invitation. So my presentation today will be on multidisciplinary collaboration in biomaterials research. I did not ask for the reason for talking about this particular topic, so I understand it's for the joint project. Now I actually addressed this a little bit from the philosophical perspective, also from the viewpoint of the importance of multidisciplinary collaboration, and I just gave two examples of the type of research that I'm doing. So my base is the Biomaterials Research Laboratory at the Faculty of Material Science and Applied Chemistry at Riga Technical University. So why collaborate? Can't we do everything ourselves? I think it's great to talk to people from different areas because they have new ideas, they have a different perspective on matters. And so even when we've been taught about the same topic, the way in which we see that topic is totally different. And this can, through discussion, provide some new ideas, some new approaches and some new solutions. It's an opportunity to assemble expertise so that you can collectively solve problems. You can combine the knowledge base and the capabilities. And this is something which isn't usually stressed sufficiently, the knowledge base and the capabilities. It's usually just, the emphasis is just put on the tools. Okay, what piece of equipment do I have in my laboratory? But I think it goes further than that, because every person who has been working very actively within the area or within science knows of a big pool of information and can contribute to discussion in a much richer form. So the contribution may be at a consultant level, where you just give the information, or at a creative level, where you try and solve problems, try and make better equipment, better tools, try and make better materials. As a materials engineer, I'm always looking for ways of getting better testing techniques, making better materials, or making sure that they have a better performance. Okay, so there are three aspects that I'm continually looking at. We need to collaborate so that we can use resources in a new setting with a new angle of inquiry. I mentioned that before. Give each other some new experience. Okay, so you're typically accustomed to talking to physicists. It's always good to get out of the physics pool and talk to chemists, talk to material scientists and engineers. Now, I've got people smiling at me because, yeah, I'm talking in a different way. Maybe I've got a different viewpoint, and that's the excitement of, again, collaborating and coming together. And finally, we've got pressure from the EU to work together. Okay, so our collaboration should be not only amongst scientists, our collaboration should extend to industry. Okay, so we should be actively looking for industrial partners that we can work with. So the partners for collaboration, they could be content experts or technical experts. When you're looking for partners, there needs to be time. They need to have time, the partners, and they need to have an interest. Okay, if they don't have too much time, you need to understand where to capture them. Try and find out which events they attend, and try and catch them during the tea break. Okay, so that you can exchange some information. You need to make sure that they're accessible so that they can discuss some topics, some themes, some problems that you may have. And naturally, look for people with complementary skills. Okay, if you understand the problem that needs to be solved, try and identify the different components, the different expertises which need to come together to solve that problem. The form of collaboration, it can be merely providing access to resources, it could be equipment, okay, it could be special materials, or at another level, there may be an exchange of information. Okay, where people need to give lectures. Okay, so this is the first form of exchanging information from me to you. There may be practical classes where after lectures you go to the laboratory and you do some practical experiments. Okay, because during the practical experiments, during the practical work, people can identify with what needs to be done a lot more easily. And at the third level, you will generate new projects. All right, so I suppose what we're trying to do is trying to look for people, trying to look for resources. So identify the resources which are available both within Latvia and within the neighbouring countries. How to start a collaboration? Well, first of all, you meet people, you share ideas, you propose solutions, and if you still see a sparkle in the other person's eye, then you know that you can continue that. You try and document the new ideas, and then you play ball with this document. You send it to the other person, you get their ideas, they send it back, you try and develop that idea a little bit further. At that point in time, you may brainstorm and try and look for different solutions in solving the problem. It's very important to know where there is the need, or what is the need. And if we're thinking about collaboration, it needs to be matched with the European Union needs. Why? Because they're going to give the money. So identify the needs from the European Union very, very, very quickly, and then see how you can solve those problems. There's two levels. There's two levels of activity. There could be merely an academic exercise in developing a particular area of science, or there could be a need for industry, so that may be merely application of new knowledge to the industrial setting. Very important that the person assesses the state of the art within the field, and that can be done by conducting a literature survey, a market survey, and a patent search. So, multidisciplinary collaboration. I was just in Finland, so I was on the phone to Arnolds, and Arnold says, "Oh, you should be giving a talk tomorrow." I said, "Oh yes, I missed that email." I was there in Finland giving my students some experience in Tampere University of Technology. So I've got Eva Denki, presently an exchange student from Australia, so she's using a sectioning tool. And there's Lena Pudum, my doctoral student, who's using the auto polisher. Okay, so the collaboration there is very important because they get additional experience. And that experience gives them a different setting, a different knowledge base, so that they can be more enriched within their work. The type of work which is happening within the Biomaterials Research Laboratory is merely within the design of materials. We take inspiration from nature. Okay, we study all the different types of materials, ceramics, metals and polymers. Examples of our collaboration are the following. We collaborate with the Atomic Spectroscopy Institute and Valsburg in Latvia. We also collaborate with the University of Oslo in Norway, Faculty of Chemistry in Latvia, Tampere University of Technology in Finland, where we were just this week, University of Adelaide in Australia, and each of those have got a complementary field of expertise. There are other projects which we do have that are very active at the moment, but I just haven't mentioned those. I just want to highlight two examples. Okay, so we are accustomed to certain standards which are available within industry. Those standards may not be at a sufficiently high level, advanced level, where we can continue to make advances within science. And so sometimes we may need to have a look at those standards and see if we can develop those standards a little bit further. For my material hydroxyapatite, we're talking here about the hydroxyl ion within hydroxyapatite. It's only there at 1.88%. There's no technique which is available for measuring this. So we had to, first of all, make an oxyapatite. And oxyapatite is very reactive. You expose it to air, the hydroxyl peak within the FTIR spectra shows that already within 2 minutes you're getting hydroxyl incorporation within the lattice. Back in the 1970s, they said, no, it won't happen at room temperature. Well, they never made a very clean oxyapatite, and they didn't have these techniques available for following the stability of the material. After 120 minutes, we get full stabilization of the hydroxyapatite lattice on the outside. So we have to be very careful how we process this material. And we were sitting down with Arnold saying, oh, how can we make sure that we prevent the access of moisture to the powder? He said, oh, that's easy. I looked at him, I smiled. He got out his pen and he drew a couple of pictures. And here's the final setup. So within the institute they have a very good glass blower. We got our powder, we put it inside the glass contraption, so it's at the very end. This actually goes into a cylindrical furnace. On the side we have a little ampule with New York oil. It's a paraffin-based oil. So we start off by heating the powder up to 400 degrees Celsius. We release all of the moisture. We evacuate the gases through a rotary pump, a diffusion pump and a sorption pump. And then we actually crystallize this material. We crystallize this material at higher temperature. We're still under vacuum. We fuse that shut, and then we essentially bang this ampule against the glass wall. The oil leaks out and covers the powder. It's quite simple. But previously, everyone was analysing the powder within air. They did not understand that the water, within 2 minutes, was already changing the powder. So this is a new technique which we hope to publish soon within the literature, and could be available to the people within the field. Another example is looking at the surface characteristics of the material. We're talking about hydroxyapatite-coated dental implants. Hydroxyapatite-coated dental implants typically are very rough. If we have a look at what's available within industry, very rough surfaces. Okay, got a collection of smooth areas and micro-rough areas. This is a lot smoother, very large variability. So there's a need to both refine the process and also to introduce more detailed topographical measurement techniques. And so we collaborated with the University of Norway that had an atomic force microscope. They were able to, first of all, we made the coating. You can see that this is totally different. It's very smooth. It's got a collection of flattened droplets. They actually provided a map. This actually is a map from Riga Technical University using a profilometer. This is a 3D map. This is a photo simulation, what you may see within a scanning electron microscope or an electron microscope. Looking from the top, here is a flattened droplet. And with profilometry, you can start to measure the profile. And this becomes interesting because we've been able to control the topography of the surface. So having these additional measures provides us a lot more insight into what is happening on the material. We've been able to establish a relationship between the droplet size and also the splattered droplet height. And we've also shown that the crystal size varies on this flattened droplet from the edge to the very core of the material. No one knew that before. Okay, but now we've got a new technique of actually scanning the entire surface and measuring the crystal size and also the micro and the nano topography. So that's an important tool which can be now used to understand how bone cells respond to the nano topography. First of all, we need to measure the topography, then we need to get the cell response, and then we need to match them together. So that gives you two examples of the type of collaboration which we have done. The collaboration, it requires extra effort, which means you have to step out of your laboratory. You have to look for those. You have to look for those people. You have to look for those contacts. And my viewpoint is it makes science so much more interesting. There's a lot of research happening within the lab, but you need to collaborate with other people because it provides freshness within the research. And you have to have a mindset of collaborating because otherwise it won't work. Always don't go very proudly into society saying I have solved the problems. Always give the benefit of the doubt and listen to other people. See what viewpoints they got. See what type of understanding they have. There's always something that can be contributed to try and improve the knowledge base. Thank you for your attention.
How we can influence the morphology of the ganglions?
How do we determine the morphology? Morphology is the shape. We were looking at the topography. We were looking at the height.
Yeah.
So
and can we influence this structure?
we can influence, yes, the process which we are using is thermal spraying, and it's not a very easily controllable process, but we can influence it. We can make the roughness be much larger. Okay, we can use flatter droplets, we can make much taller droplets, we can control the crystal size. But now what we're doing is we're trying to resort to more controlled processes, such as sputtering, which is a lot more uniform. You can control the grain size very, very easily over the surface.
Okay. We have no more time for more questions, so let's move on.
There was a lot of lucky coincidences we come together with Karlis. Karlis is our Latvian Marine Curie fellow, returned back from Australia. And why Fotonika-LV and my team come together with Karlis was single-pillar coupled plasma, where you can generate a lot of photons, but he said you can also use this temperature there for biomaterial composition and so on. And then we put together this expertise with working in quartz and glass technologies and micro technologies and so on. That was how we are doing it. But more broadly speaking, it's Karlis demonstrates as an example. We are speaking about European research area very frequently, but the main basis of European research area is this solidarity agreement among researchers in the European Union that access to research infrastructure is without demand for payment. That means economical input, economical benefits, and also research outputs. And the same, our Photonics Association, we always say we are absolutely open. Everybody who wants to work with us will be accepted.
I think that's one question.
Okay.
You mentioned the purity.
Yes.
You said we'd like to increase the purity.
We like to improve our methods of detecting the purity, and along with that goes also controlling the purity, increasing the purity. Yes, so very interesting is, I'm just looking at the hydroxyl groups right now. You can use also...
You said something about the purity you said now?
Yes, it's very variable. We are looking at the hydroxyl groups, where we have introduced new processes for optimizing, maximizing the hydroxyl content. And we're starting to do work on trying to control the hydroxyl ion alignment within the lattice so that you can produce an electrode. From this material you can produce a charge on the surface, and so from the charge you get an electric field, and now you have an implant with an electric field, as opposed to just being a material with a certain composition. So we're trying to increase the functionality, and an important part of that is to measure the hydroxyl content.